you were able to hear me through his mic sitting from here, right?
Yeah. Do you want to check it? I think it's still plugged in there.
Actually, tell you what, why don't we just jump in and go for it?
That's very brave.
Yeah, it's basically
Yeah, okay.
Groups we've got here. It's welcome to the meeting. Thank you for all our sponsors. There's a code of conduct. Here's our speaker for the evening or the main presentation. Go for it.
That's it for real?
That's it for me.
All right. Hey, come on in. It's gonna be hard to look at you all with the screen sitting here. I'll have to work on that. All right, so thanks very much for having me, and us, I should say. I'm Brad Chamberlain. If you're looking at the thing online, it says I'm Jade. This is Jade's computer. This is my colleague, Jade.
Hello.
We're going to be tag teaming tonight. I'm going to do sort of the slide presentation, and I am not ever brave enough to do a live demo, but Jade is brave enough for live demos, so Jade will be taking over for that part while I duck and cover. I'm going to be talking to you tonight about Chapel. Chapel is a programming language that we've been developing originally at Cray, and Cray was acquired by HPE around the time of the pandemic, and so we're now HPE employees. I'm one of the founding members of the Chapel project, and I've been the technical lead since about 2005 or so. And we're really happy to be here. This is actually the fifth time that we have, now what have I done? The fifth time that we have spoken at Northwest C++ Users Group over the past 12 or 13 years. And we really appreciate you having us in, every so often to kind of give you an update, particularly given that we're not about C++ necessarily, and sometimes we even might make fun of C++. Well, good. We agree on some things. So anyway, if you're a Saturday Night Live fan, they have the Five Timers Club, and so I felt like we checked that box with tonight. So appreciate you having us back. I'm going to start out talking about some of the motivation for the language, and to do this, I'm going to use some slides that I developed about a year ago. I was asked to give a keynote at a workshop that's all about high-level programming models for high-performance computing. And it was the 30th anniversary of the workshop. And so I used it as an opportunity to kind of reflect back on where have we come over this past 30 years in terms of HPC programming. And I should say, if HPC you use every day, for me, that means high-performance computing, so like supercomputers, things like that. So this first part is kind of talking a little bit about that. And as is often done in HPC when you're reflecting on the past, I looked at the top 500, which if you're not familiar with it, is a list of the top 500 systems that participated in the competition. It's published every 6 months, and it's a great way to sort of track architectural trends over the long term. And so to sort of make my job a little bit simpler, I just looked at the top 5 systems in the top 500, starting originally 30 years ago, and then looking at it in the most recent listing, which was in November. There'll be another one coming out next month. And for both of these, I basically looked at the number of processor cores on the system, the Rmax value that was obtained, which is like the performance, so higher is better for that value. And then here I've just called out who the vendors are, though if you dig into the site, you can see things about the types of processors and the network and things like that. So if you do some math here, what you can see is over those 30 years, the number of cores in the top 5 systems has increased by factors of hundreds to hundreds of thousands. And the Rmax or performance has increased by millions to tens of millions, right? So basically a massive, massive improvement in terms of what HPC systems are capable of. And this has been achieved through a number of technological changes and trends over time, such as vector processors becoming commodity, whereas before they were kind of only on Crays and supercomputers. Commodity multi-core and many-core, which of course happened over the past 30 years. Multi-socket compute nodes, which have been used more and more frequently in HPC. Those trends have resulted in non-uniform memory access within the processors and on the nodes. Our network architectures have really changed. They've become high-radix, low-diameter networks, which makes you much less sensitive to the topology than used to be 30 years ago. And then GPU computing has really come to the forefront, where if you look at the top 5 systems nowadays, most of the cycles are coming from GPUs. So lots and lots of changes in the hardware resulting in this massive performance improvement. And from my perspective as somebody who is interested in programming, I would say that most of these changes have made programming only harder. So the only one I sort of give credit to making programming easier is the network changes, because it used to be you would really optimize for like it's on a hypercube or it's on a 2D grid or something like that, and really think about your messaging. And now you can mostly just sort of focus on local versus remote and not worry so much about where the processors live on the network. So that's really great. But all these other things have made us be more sensitive to vectorization, to parallelism, to locality, to being able to program GPUs at all. And so by and large, the programming landscape has become more complex. All right, so speaking of the programming landscape, what I'm going to do next is reflect on where were we 30 years ago versus today in terms of the kinds of programming models used in HPC or the notations we use. And so if we look back, again, 30 years ago, the languages that were in use then in HPC were Fortran, C, and C++. And if we look at what is being used today, it's predominantly still Fortran, C, and C++. Clearly, if you pay attention to the mainstream, languages have evolved rapidly, right? We have Go, Rust, Python's become majorly dominant. But in HPC, we're really kind of stuck in our ways here, arguably. And I would say not necessarily for the better. Back then, to communicate between nodes, we used some libraries called MPI, PVM, and SHMEM. Have any of you ever used any of these three libraries? These are basically ways to communicate between processes. Little MPI or? Okay. Okay. And today, more or less, those are the same. PVM sort of fell off at some point, but MPI is still very dominant, and SHMEM still has strong supporters as well. For internode concerns, so like, well, back then it was mostly kind of vectors, but nowadays, multi-core kinds of parallelism. Back then, we would have used pthreads, vendor-specific pragmas and intrinsics. And OpenMP, in my mind, I feel like it's about 30 years old. It's actually more like 28, but it was, it was on the cusp of coming out and has become pretty dominant since. So today it's pretty much pthreads and OpenMP, and then this library from Sandia, I want to say, Cocos, has also started being used. And then for scripting, hello. For scripting, back then, Perl, various shell scripts, and TickleTK. And nowadays, Python has supplanted a lot of that, which I think is a great productivity bonus. And Bash has taken over most of the shell scripting. The one other big change that's happened in programming here over the past 30 years, which I alluded to before, is the fact that GPUs have come on the market and really dominated. And unfortunately, despite having all these nice parallel notations, none of them were really up to the task of programming GPUs. So now we also have CUDA and HIP and SYCL and OpenMP and Cocos and OpenACC and OpenCL and a host of other things, as we all sort of wrestle with how do we program GPUs and program them effectively. So if I color code this to kind of show the diff, a couple things have gone away. A couple things have come on board, primarily GPUs and the scripting notations. But by and large, I would say our software notations have largely stayed the same in HPC over the past 30 years. Again, with GPU computing being the big differentiator and the scripting becoming more modern as well. And I think most notably here, HPC has really failed to broadly adopt any new programming languages. So to me, that matters because I feel like we have been living and we're still living in a time where it's really analogous to when Fortran was first introduced and everyone did assembly programming all the time. You were used to kind of doing everything very explicitly, moving things around the memory hierarchy, things like that, into registers, out of registers. And in HPC, we're not at that level, but we are moving values around between memories across different compute nodes or from the CPU memory to the GPU memory. So in the same way, I feel like we should have languages that take care of those kind of details for you, abstract that away, and give the compiler the opportunity to optimize a lot of that stuff, where today, again, we're doing it mostly manually. And so that's kind of, a little bit of a statement about like what Chapel cares about. The other big change over the past 30 years is 30 years ago, like when I was in grad school, if you wanted to do parallel computing, it was pretty much on HPCs or nothing at all. And HPC systems were at national labs, maybe large universities and industry, but not, everybody wasn't parallel computing. It was pretty niche. And nowadays, of course, things have just expanded dramatically, right? You've still got the traditional HPC systems in the traditional places, but all of us have multi-core on our laptops and desktops. In fact, you could hardly buy a single processor anymore. We've all got GPUs. So there's kind of parallelism everywhere. And then meanwhile, cloud computing's come about, and that's kind of like supercomputers that you could rent time on if you want to look at it that way. And of course, AI data centers have become the big thing, and they've dwarfed a lot of the traditional huge HPC centers. So parallelism is now everywhere. But unfortunately, I don't think our programming models have really kept up with that trend. All right, so that's kind of my motivation for Chapel. Chapel, again, this language that we work on, I describe it as a modern parallel programming language. By modern, I kind of mean post C++. It's portable and scalable, so it runs on this laptop up to the largest supercomputers. It's open source. We do all of our development on GitHub. Like any good open source project, it's collaborative. We get contributions from users in the community. And as of just about, 7, 8 months ago, we are now a member of the High Performance Software Foundation, which is itself part of the Linux Foundation. And so we've become a Linux Foundation project, which has been exciting. I'll talk a little bit more about that later on. And at the highest level, you can think of Chapel as having two goals. One of them is to make parallel programming, to support general parallel programming, by which I mean, if you have some parallel algorithm in your mind that you'd like to express to your computer and some parallel computer to run it on, you ought to be able to do that in Chapel, or we're not succeeding. Like if you hit a point where you're like, well, it was good while it lasted, but now I want to do this, I need to go back to MPI, then we failed in that regard. And the other one is to make parallel programming at scale far more productive, which I'll talk about a bit on this next slide. So if we go back to my 30-year retrospective slide and kind of focus on the present, the vision for Chapel is where today we're using like a serial language, or at least a traditionally serial language, communication for internode, something else for internode multi-core, and then something else for GPUs. The goal of Chapel is really to kind of supplant all of those and in one language just take care of all of it. So you're programming all these different levels of parallelism within a single unified language that a compiler can optimize. And not only that, but that you can target all these different kinds of parallel systems, from multi-core laptops to supercomputers, the cloud. We don't have experience on AI data centers, but I think that would be an interesting thing for us to look into as well. And the key to doing this, in my mind, is really to design a language that talks about parallelism, like what should run simultaneously, and locality, which is to say, where should things run and where should things be allocated? And to sort of abstract away all the details of, are we launching GPU kernels? Are we communicating through messages or RDMA? What kind of threads are we using? That kind of stuff shouldn't be kind of part and parcel of everything you code. But again, today in this sort of pseudo assembly world we're living in for HPC, it often feels like it is. All right. So in this talk tonight, we've got, three main goals. So one of them is to motivate Chapel, which I've just done a bit of, and introduce it for anyone who hasn't been to our past talks, or it's been a while since we've done one. If your memory's like mine, you need a refresher. And then we're going to highlight some of the key milestones and changes since our last talk. So some new performance results, talk about GPU programming, which was just kind of on the cusp of coming out when we last talked 4 years ago, but now is much more full-featured. Talk about a few user applications, Chapel 2.0, which is a release we did a couple years ago now, and the High Performance Software Foundation that I mentioned. So these are some of the kind of headlines from the past few years. And then at the end, we'll talk about how you can learn more if you or someone watching this online is interested in that. And so I'm going to dive right in. Is anyone here not a programmer or not a programming language enthusiast? Guessing you all are. Okay. So I'm going to do what I would want to do in a talk, which is not just hear sort of platitudes, but to see some code and dive right into an example. And the example I'm going to use is one that's called Bail Index Gather. This is a fairly simple computation, but it's sufficiently non-trivial on distributed computing that I think it makes a good introductory example. Sort of you can express in a few lines of code, and yet it's not completely trivial. So what I've got here is a source array. It can be sort of an arbitrary size. And I've got a destination array, which could be a completely different size. And here I've illustrated it as though it does. And then I've got an indices array, which basically is going to tell me where do I want to gather data from. And so to implement this, I'm basically just going to go through the indices array and say, okay, well, the first element should get element 3. So I'm going to go out to element 3 in the source, copy that into my destination. The second one is in index 7. So I go over to index 7, grab that, store that. And of course, because we care about parallel computing, I don't want to do this one at a time like I'm illustrating, but I really want to go out and say like, okay, like everybody, what are your indices? And let's go grab those values as quickly as we can. And not only do I want to do it in parallel, but I want to do it in distributed. So I'm just going to sort of illustrate this in this cartoon with this dotted red line, which is like maybe I own half the data, you own the other half. Sometimes I'm going to need to read your data, you're going to need to read mine, and we need to make that all work out. All right, so let's look at some code that implements this. Oh, actually, before we do that, I'll say, a lot of people look at this and say like, well, like this doesn't resemble anything I've done. Why would I care about this? And I guess I would say shuffling data around on distributed systems happens a lot, whether they're stored in literal 1D vectors like this or something more complex. shuffling elements across the network element by element has kind of a lot of overhead, because a lot of the overhead in HPC is just communicating across the network, not so much how much you're communicating. So you typically want to amortize those overheads. And so you can think of this as like maybe you're just fetching things from remote addresses, or it's like a big key value store you're fetching remote values from. Anyway, a lot of patterns you can think of as being this sort of like fetching a lot of data remotely. All right, so looking at this in Chapel, I'll start with just some simple declarations here. Let's see if I point here. Yeah, okay. So up here, I've got a couple of constants, n and m. These are just going to define the problem sizes of my arrays. And then this is the notation for declaring arrays in Chapel. The colon notation basically is going to indicate, I'm going to give you the type of this variable, and the square brackets say it's an array, and the indices are within here, and the element type of the array is an int. So this is a n element and then two m element arrays to give me my source and indices and destination. Chapel is a compiled language, so I can compile this code by invoking the compiler, which is named CHPL, compile it like that. And then when I run it, I can specify how many locales do I want to run on, which you can think of as compute nodes, essentially. And here I've said, let's run on 4. And so I have this little cartoon down here where I'll kind of show what resources we're using as this executes. And initially for these declarations, I'm not doing anything that is parallel or distributed. And so really it's just the single core on locale 0 executing this and allocating some data in its local memory. All right. These constants I declared up here have this config keyword on them. And what that does is give me some nice sugar so that on the command line, I can basically override their default values. So I didn't have to do any argument parsing or anything. I could just say, let's run on million-sized arrays. And suddenly my source, destination, and indices arrays are much bigger. So that's what that config keyword is. It basically gives me this built-in argument parsing to change the default values of things. Next, I'm going to initialize my arrays. I'm going to use this random module that is one of the standard modules with Chapel. And I'll use this little loop expression using these square brackets to initialize my source array, basically just putting in a little ramp of values there. And then I'm going to call this fill random routine in the library to fill up my indices array with some random values. And here, both this little loop expression and this fill random routine are parallel operations, but they're iterating and computing over just local data structure and values. So here you can see my diagram. I'm using all 4 of my cores, so I'm getting some parallelism, but it's all parallelism that's constrained to one node right now. And we'll look at how we make it multi-node as we go along. Any questions here so far, though, before I go on? And I should say at the beginning, anytime, feel free to raise your hand if you've got a question. All right. So next, let's actually do the computation. I'm going to write this a couple of different ways. And the first way I'll do it is just using a serial loop that iterates over my destination indices, reading the corresponding index and using that to access into my source array. So this should look, not that different from what you'd write in C++ or other languages. And because I use the for keyword, this is going to compute these one at a time. So I'm, again, only going to use one core because I haven't done anything parallel here. A second way I might write this, and the way I'm going to use it for most of this little demonstration, is to use what we call a zippered iteration. So my destination array and my indices array both have the same number of elements. So I'm going to say, let's just iterate over both of those in lockstep. Take the values out and call the destination location D and call the index I, and then use that to write it. This is exactly equivalent to the previous. For some reason, when I originally did these slides, I wrote it this way, but you could use any of these, and everything else I'm going to talk about is basically equivalent. So let's start looking at some parallelism. The first thing I might do is use this for each loop. This is the first parallel loop form we'll see tonight. And for each is a loop form that says, I assert that this loop is parallel and should be run in parallel, but I don't want you to spin up any new threads or tasks to execute it. I want you to execute it only using the resources available to the current task. And so what this will do is give you like vectorization of the loop, for example. So if you're on a vector processor and the loop is vectorizable, this says like, hey, this should be safe to vectorize. Go ahead and do that if you're able to. And so we'll get some performance improvements probably, but you'll see in my picture here, I still only have a single core running because I haven't done anything with multiple threads or tasks. However, if I change that keyword from for each to for all, there's obviously a little bit of learning curve to remember which is which. For all says, as you're iterating over these things, use an amount of parallelism that is appropriate for the iteration. And the things you're iterating over themselves are the things that get to decide how much is appropriate. So for example, in this case, I'm iterating over these arrays. They're both local arrays. And so they say, well, to iterate over a local array, a good thing to do is spin up a number of tasks equal to the number of cores and divide up the iterations across those tasks. So like in this diagram where I have 4 cores, I would say, okay, well, let's spin up 4 tasks, give them each a quarter of the arrays, and have them do that in parallel. And again, you can see in my picture here that now I've shown all 4 cores are engaged with the computation. For my small problem size of 10 and 4 here, that's probably overkill. But if we used 1,000,000 or something like that, this would give you good multi-core parallelism. Go ahead. Yeah, so the question, I don't know how well people can hear on the recording or online, but the question was, is that a dynamic choice of how much parallelism to use? I guess I nodded, I said yes, but it's kind of a combination. So the static piece is, what am I iterating over? And that collection, like in this case, the array, has the ability to say, like, here's how you should iterate over me in parallel. And user-defined data structures can do this as well. You can define, like, here's how you run a for all loop over me, basically. And so the decision of what algorithm are we going to use to implement the for all is static because it's part of the type of the thing you're iterating over. But the details can be dynamic. So we can sort of dynamically see, well, how many cores are on this node? Or we can even see, like, how many unoccupied cores are on this node. Like if we're in an inner loop, maybe there's already some parallelism going on. So maybe we're going to say, like, oh, well, we shouldn't parallelize because there's already all the cores are fully engaged. You could even do things like dynamic load balancing the iterations or things like that. So yeah, static choice of algorithm, but the algorithm itself can make dynamic choices. Yeah. Any other questions here? All right. Next, I'm going to show you another equivalent way of writing this. So I should say I didn't show this on the slide, but going back to the original way I wrote it, where I was just looping over the indices and just doing indexing, you could do that with the for all as well. One other way you might write it is using this sort of whole array notation, where I'm saying the destination array is equal to the source array indexed by the indices array. This is exactly equivalent to that for all loop. And what's interesting here is that in Chapel, this is basically like normal scalar indexing and more or less normal scalar assignment. When you call a scalar operator or a scalar function in Chapel with an array, you get automatic parallelism. So if you define your own function foo that takes in an int and I pass you an array of ints, that will be executed in parallel as though it was with a for all loop. So this is probably the most compact way to write this. But again, for whatever reason, when I made these slides, I wrote it this way, and I'm too lazy to actually update the slides, apparently. All right, so now we're back at my sort of canonical approach. So the next thing we're going to do is change this from a single node parallel computation, a multi-core computation, into a distributed memory computation. And so what we're going to do, I'm going to do this in 2 steps just to kind of make it super clear. The first one's not going to really change anything. It's more or less a code refactoring. What I'm doing here is I'm taking these anonymous index sets that I used to declare my arrays originally, and I'm naming those. In Chapel, we have this type in the language called a domain. This is basically like a first-class index set. So it stores indices, in this case, just 1D indices, but domains can also be multidimensional or associative or sparse. And then I've basically used those named index sets to define my arrays now, right? So this is exactly equivalent to the previous code. I've just done some naming there. And this can often be nice because it means, like, if I wanted to loop over those index sets, I can now use the name instead of typing 0 to n, 0 to m everywhere and potentially making mistakes. But the reason I did it here is that the next thing I'm going to do is use this standard module called block distribution, and then use the block dist type that's defined by that module, call a factory method, create domain on it. And basically what this is going to do is take those indices and block distribute them across all the compute nodes I'm running on. Again, for my little 10 and 4 example, this isn't very interesting, but running on a full problem size will basically take those arrays, chunk them up evenly between all of my compute nodes, give each compute node its independent piece of it. And you can see this with my little diagram. Now all of my little orange memories have array elements stored on them. And then when I run the for all loop over it, now I'm running it over a distributed array. So again, the static recipe says, like, oh, I'm a distributed array. What you should do for me is launch tasks on all the nodes that own a piece of me, use all the cores that are free on each of the nodes that has a chunk of that, and do all the iterations in parallel. And again, you can see that in the diagram. All of my cores are now spun up, right? So the thing I want to make sure is super clear here and really exciting, I think, is that, again, this is a very simple computation, but the science of my computation, if you will, the for all loop, basically didn't have to change at all. All I had to do was change a couple of declarations, and I've changed this from a multi-core laptop single node program into one that can span, in this case, 4 or thousands of nodes. And I think that's the power of these domains and these distributions is modify some declarations and the program behavior will change dramatically. All right, so next let's look at kind of how this actually performs in practice. I'm going to throw a couple of compiler optimizations here which enable the performance results I'm going to show you. FAST basically just turns off a bunch of runtime safety checks, sort of like taking the seatbelt off, turns up some optimizations. And auto aggregation is an optimization that I alluded to earlier. You don't want to really be communicating an element at a time. And this is an optimization that'll look at for all loops like this and basically batch up a bunch of updates that need to be done and then send those across the wire all at once. If you don't do that, it'll still work. It'll just be much finer grained communication. I'm also going to dial up the number of locales here to 4096. My cartoon disappeared because I don't want to draw that many. And I'm going to turn up the problem size as well to match. And so what I'm showing here is a performance graph. So this is gigabytes per second. So higher is better. And on the x-axis is the number of compute nodes I'm running on, where at the top here I'm running on 4,000 some compute nodes. And this is over 500,000 processor cores. The blue line is the Chapel performance. You can see as I add compute nodes that the performance is improving and improving. The green lines down here are the reference versions of this benchmark. These are written in SHMEM, which is one of the conventional HPC programming technologies I mentioned before. It's basically a way of communicating between processes as though we shared memory through a library API. So you can do things like put things into a remote address or get things from a remote address. And these versions in particular are using these abstractions that are built on top of that called XStack and conveyors, which do that same kind of communication aggregation that I mentioned our compiler doing. But here it's the programmer doing it explicitly through these abstractions in the library. So those result in these green lines here. You can see that we're both outperforming them, and also they stopped working at some point due to limitations in the library or the use of the library. And so we were able to scale much further. And I've obviously left out some of the declarations here, but this Chapel loop here is essentially equivalent to this amount of SHMEM code here. So a lot less code, better performance, better scalability. One other thing that's happened just in the last couple of months is we've had a colleague at Oak Ridge look at how does Chapel do not only in terms of performance for this computation, but how does it do in terms of memory usage? Because more and more as these systems get really big, as you hear about in the news with AI data centers, there's a lot of concern about how can we reduce the amount of energy required. And this is a very complicated visualization, which I'm not going to teach you about all at once. But what this is doing is comparing Chapel in the yellow to conveyors, which is one of those SHMEM implementations in the purple. And on one axis, it's the ratio of their speeds. So to the left is faster. And then the other axis is energy usage, the ratio of their energy usage. So up is greener. And the three plots here represent three problem sizes. So the biggest problem size is over here. And this is running on from 1 to 64 compute nodes. So you can see that with the smaller problem size, it's kind of a mixed bag. We win some, SHMEM wins some, which is to say some of the points are in yellow, some are in purple. But as the problem size grows, Chapel starts winning both in terms of performance and in terms of energy usage. So this is, again, a result that's just from last month, actually. It was presented at the Cray Users Group meeting, and it's hot off the presses, and we're pretty excited about it. I think there's more we need to do here to dig into it, but we were pleasantly surprised to be coming out on top here on the bigger problem sizes. So to summarize this kind of introduction that I've given you so far, Chapel supports language features for data parallelism. We've seen that in a number of ways. The for each loop, which gives us the vectorization, the for all loop, which gives us multi-threading. The square bracket loop we saw briefly when I was initializing my arrays. Again, that's equivalent to a for all if the thing is parallel. If it's not parallel, it'll fall back to a serial implementation. And we also saw briefly these whole array operations where we basically are taking scalar operators and promoting them across arrays. And again, that gives us parallelism as well. So those are 4 ways to express data parallelism. We've also seen parallel zippered iteration where we're iterating over multiple things simultaneously in parallel. That's actually a really interesting challenge. Like if 2 collections have very different ways of iterating, how do you zip those together? I'm not going to talk more about that tonight, but that's something we've written papers on. We've also seen these distributed arrays where with a slight tweak to the declaration, I've changed a shared memory code into a distributed memory code. And as you've seen, these results, these features result in good performance, good scalability, and as we've seen in these latest results, also nice energy efficiency. So this is a great place for me to pause and see if there are any questions so far. Next, we're going to be going into some of Chapel's lower level features and some of the new support for GPUs that I mentioned. Question, yeah.
Yeah. So if after 30 years people are still using Fortran, C, and C++, what are the barriers that are preventing everyone and their dog from rushing to adopt Chapel?
Adopt Chapel. So I'm going to come to that at the end of the talk, because my hope is that you'll be like, oh, this seems pretty cool. Like, yeah, why hasn't this taken over the world? I'll say for one kind of short answer to that, even though we've been working on Chapel for, I think it's 20 some years now, like for a lot of that period of time, it was a research project. We were building everything from the ground up. So for years, when people came to us, we would say, no, don't actually use Chapel. Well, try it, give us your feedback, but like, don't build your next application on it. And it was really sort of in the, I would say 2018, 2019 timeframe, we really started telling people like, yeah, like you might think about using it now if you're like sort of an early adopter kind of personality. And so in fact, a bunch of the applications I'll show you tonight came about just sort of since 2019, more or less. But yeah, there are other factors as well. And again, I'll come back to that. We could talk about it more towards the end. Yeah. Yeah, so question, I forgot to repeat the earlier question. But for this one, how do the instructions get distributed? So what's going on under the covers is, even though the model here is that the program starts running as a single task on locale 0, what's really going on under the covers is we compile the binary and launch it on all of the compute nodes. So they all have a copy of all of the code that's been compiled into the program. So the copies are actually received by kind of the system software. There's sort of a launch mechanism, like Slurm is typically used, where I say like, launch my binary on all these nodes. So that happens, they all start running. And then all of them are orchestrated, they're parameterized by like a unique ID and the number of copies. And all of them basically set themselves up, but then go to sleep waiting for work, except for locale 0 that starts running the user's main. And then as the program hits things like a block distributed array declaration or a for all loop over such an array, then that locale says, hey, everybody, wake up. We're going to execute this routine that the compiler's embedded in the generate code that's going to declare the array, or that's going to iterate over it and do this index gather computation or whatever. So there's sort of this constant kind of creation and destruction of parallelism as you hit parallel constructs in the code, but everybody has all of the code that is going to be used to execute that program. Yep. So it's a lot like an RPC. We call them active messages. And yeah, so you're sort of sitting there waiting, and I say like, hey, like start running your piece. You're like, yeah, I know I own these indices. I'll go run over those now. And then you say, okay, I'm done with my piece. Once everyone's done, we go on to the next statement. There's also asynchronous. So you can launch things off and not wait for them, but we won't see much of that in tonight's talk. I'll also mention one of my teammates is currently working. So this sounds like a very static model, right? Like all the code I said is compiled into the binary. I wanted to mention one of my teammates over the last few months has been working on adding dynamic loading support, which is a really interesting challenge because, you know, unlike a desktop, you have to kind of load that library on every node and make sure that we all sort of understand like what the base address is and what the offsets are for the routines and things. So there's a lot of re-architecting of our runtime that's taken place to support that dynamic loading. But it still kind of relies on us all sort of knowing we're loading more or less the same thing. Okay. All right, let me just check my time. 7:04. We started at 6:30, right? Yeah, okay. Just making sure I don't blow the schedule here. All right. So what we've been seeing so far is what I call high-level Chapel, the data parallels in these nice for all loops distributed arrays. Next, we're going to look at low-level Chapel. And the reason I put that into air quotes there is that my hope is you'll look at it and say like, oh, well, that's not that low level. And compared to things like pthreads, it's not. But for Chapel, it is. And this is going to be our bridge into talking about GPUs and how we support them. And then to that point, we'll have Jade give a demo of some live Chapel, including running on some GPUs. So we've already kind of seen this cartoon. I sort of switched the order I normally talk about it at the bottom of some of my slides. And this is kind of my cartoon for how to think about parallel computers We've got our compute nodes here. They each have some processors and some memory. And I would say that anytime you're interested in scalable parallel computing, I've already kind of alluded to this. The two main things you need to worry about are what should run simultaneously? Like what computations do I want to run at the same time? So here I've got a little picture of a sequential computation, but maybe I have some parallelism. So maybe I can use all 4 cores on my compute node. Or maybe if it's 4 with parallelism, I should be using, I forgot how this goes. So the other piece is locality, like where should tasks run? So maybe all those 4 tasks shouldn't be running on one compute node. Maybe I should put 1 task per compute node. Or really maybe what I want is 4 tasks per compute node. And so it's sort of like, how much parallelism do you want? And then where do you want things actually running? And then the same thing's true with data. I want to allocate a little array. Do I want to allocate that in the memory of 1 compute node? Do I want to distribute that array so each compute node owns a disjoint slice of it? Do I want to replicate it in some way so that everybody has their own copy of it? And these questions of, where should the data be allocated are really key. And the reason, if it's not obvious, is because anytime you have to refer to remote data, it's kind of a high latency operation. Think about going to main memory as being expensive, like it's even worse when you're going across the network. So being really sensitive to where are things running, where is data allocated, making sure they're co-located is really important for getting good performance. And so in Chapel, we have this built-in type and these values called locales. We've already kind of seen that earlier, I guess. And a locale basically says, this is a chunk of the system that I'm executing on that has some processors, so it can run things in parallel, and it has some memory, so it can store variables. And we really don't say much more than that about locales. So the idea is to make them a very flexible kind of concept that could be mapped to lots of different types of hardware. And again, this is kind of trying to abstract away all the details of the hardware from every line that the programmer writes. For today's talk, we're going to think about each compute node as being a locale, but in practice, it could be done in different ways as well. So I'm going to call these locales from now on. And there's some built-in features in the language that let you reason about locality. So here I've got a little diagram where I'm running a task on locale 1, and I've got a little array allocated on locale 2. And so I'll tell you about 3 features that are useful for reasoning about locality. The first is every program has a built-in array called locales, and this is basically just an array of locales representing the compute nodes you're running on. So on my command line, if I say run on 4 locales, this array will have 4 elements. Each of those elements corresponds to one of my compute nodes. And though I don't show it here, you can do things like use this to introspect about your machine, like how many cores does this compute node have, or how much memory does it have, or how much free memory does it have? So it's a nice way of kind of modeling the system resources within the language itself. Yeah.
Local memory versus fetching over the network.
Yeah, so the question for anyone online was, can you use locales to basically query things like what is the latency for a remote access or something? We actually don't have an API for that today, but nothing would prevent you from doing it. I would say, I think the main reason we haven't gets back to those high diameter, or no, sorry, I lost my phrase. High radix, low diameter networks I mentioned, where people used to be really sensitive to like, is it 1 hop or 2 hops or 4 hops? Nowadays, it really is largely about local and remote a lot of times. You might still care about the ratio of local versus remote, but as I say, not something we're exposing today and not something users have requested, but something we could. And I think one of the nice things about locales is there are a lot of queries you might support that we don't support today, and it's a great place just to tack in things to ask more questions about your system. Yeah, so this question is about kind of like, if I'm on a heterogeneous system, can I take advantage of that? Like maybe one locale has more cores or more memory or something than the other. I'll say that, so nothing in the language sort of restricts you from having that kind of heterogeneity in the locales that you're running on. I'll say that a lot of our standard libraries tend to assume homogeneity, kind of for simplicity. So like the block distribution we saw before is going to evenly chunk things up across the locales, even if your locale is like twice as powerful as mine. Now you could write in the, so the block distribution is not built into the language, it's part of the library. You could write your own kind of, het block dist, for example, that sort of looked at the locales and did kind of a load balancing to decide how much to put on each one. And in fact, Jade's demo later is going to show a similar kind of heuristic where you're dividing things between CPU and GPU resources. You probably just don't want to do it 50-50. You could bake those kinds of things into distributions, but I would say that most of the systems we run on, most of our users are typically running on pretty homogeneous supercomputers. And so we haven't invested a lot in going down that path. But again, sort of language doesn't prevent you from doing those kind of things. But our libraries tend to make simplifying assumptions. All right. So locales is this array of locales representing our compute nodes. Another thing we've got is this built-in identifier in the language here, which basically says, where am I currently running? And so there are a bunch of ways in which your task might move around on the system. Maybe you're in the middle of a for all loop or something, you don't know where you are. Here's a way just to kind of take stock of like, which locale am I currently running on? So for this little task, it'd be this locale1. And then for any expression that has storage associated with it, you can say, what locale is this expression stored on? So in my example here, with my little array A, I can say A00, which locale owns that? And it'll say, oh, well, that's on locale 2, for example. And so you can use these things to reason as your program is running about where are the tasks, where's the data, and as we'll see in just a moment, you can move the tasks to where the data is or copy the data over to where the tasks are. All right, so let's look at a very simple example that makes use of locality, again, using the low-level features. So the first thing, I think we mentioned this in passing earlier, when you start running a Chapel program, the user's main, if you will, is going to start running on locale 0. So this first line, right line, hello from locale here.id, again, here says, where am I running? And so Chapel is just defined so that all programs start as a single task running on locale 0. So this is going to print out hello from locale 0 because that's where it happens to be running. When I declare an array and not a distributed array like we saw earlier, or really when I declare any variable, the semantics are that the variable is allocated in the memory local to wherever that task is running. So I'm running on locale 0, so when I declare this little 2x2 array, that's going to be stored in locale 0's memory. So the next thing I'm going to do is run a for loop, and I'm going to iterate over my locales array. And so basically this is like iterating over my compute nodes one at a time. And within the for loop, I'm going to use this on clause. And the on clause says, migrate this task to wherever the expression that the on clause is taking as argument says. In this case, I'm just naming a locale, but you can also use this in a data-driven manner. So you could say like on a sub I, and it would go wherever a sub I is stored. So in my first trip through this loop, I'm just on locale 0. So this is basically saying on locale 0, well, I'm already there, so I'm just going to run it myself. And the body of my loop is very basic. I say declare a variable B, make that a copy of A. Again, I'm running locally, so I'm going to allocate B locally, probably do a mem copy to copy those values over. Then I leave that scope, B is deallocated, and I go on to the next iteration. Next iteration is a little more interesting. I'm now on locale 1. So I say, OK, now I'll start running on locale 1. We logically transfer the execution over here. As we were talking about earlier, this is going to be done through an active message. I'm going to say, hey, start running the body of loop number 0 in our program or whatever. Now that we're there, when we declare a variable B, well, we're running on locale 1, so it's stored in locale 1's memory. And now when we say B equals A, we're going to remotely fetch the values of A over to B. This won't be a mem copy anymore, but it'll be some sort of distributed copy depending on what the network supports. And then we continue through the rest of the locales, go on to locale 2, go on to locale 3. And then as we finish, we've left the scope of all of them, so all the arrays are deallocated, and we're back in locale 0 where we started out because we've left that scope. Hopefully obvious, this is a distributed program. I'm moving between these different compute nodes. But as you noticed, it's serial, right? I'm kind of just doing them one at a time. And I think this is a really crucial property in Chapel is that there's parallelism, what should I do simultaneously? And then there's locality, where should I do it? And so here I've done that serially. To do it in parallel, I'm going to use another form of parallel loop we haven't seen yet called a coforall. A coforall is like a for all loop in the sense that it's a parallel loop. It says do all these iterations in parallel. But where the for all says use the appropriate amount of parallelism depending on what I'm iterating over, the coforall literally says create a distinct task for every iteration. So in this case, I'm allocating over my locales array. I'm going to create a task per locale or per compute node. And in this specific case, I've got 4, so I'm going to create 4 tasks. Each task is going to hit this on clause. So I basically move each task out to its own corresponding compute node. It's going to declare its variable B. They're all going to make their own copy of that. We'll then leave the scope of that on clause. B will be deallocated, and the tasks will collapse back down to locale 0 again. Obviously not the most interesting computation here, but gives you the idea of some of the mechanical things that are going on at the low level in Chapel. I mentioned earlier in response to your question that you can write your own distributed arrays in Chapel. Underneath the covers, what's happening is things like describing parallel iterators that are doing things like these coforals across the locales and then coforals across the cores within a locale, dividing up the work between those. So creating those higher level abstractions like for all loops and distributed arrays is all done in terms of these lower level features. All right, and now to transition to GPUs. So suddenly with GPUs coming on the market and becoming broadly adopted in HPC, my simple diagram of the locales becomes much more complex because now I have two different types of cores, maybe multiple GPUs per node, potentially two different kinds of memory, though I've drawn them the same here. And so what we do in Chapel is we think of these GPUs as being what we call sublocales. So each of my top level locales has an array of locales called, which is named GPUs, and those are of a different locale type that correspond to the GPU's processor type and memory type and things like that. But then we can use the exact same language constructs to target them as we did for the top level locales. So I can say like on here.gpu0 and run something on the first GPU on my local compute node. Or I can do a coforall across all my GPUs and an on clause onto those GPUs to create a task per GPU, for example. So again, same abstractions for parallels and locality, just being applied to the multiple GPUs on a node rather than the multiple nodes on a network. If we go back to my Bail index gather, sort of just a simple example of this, if I take this declaration of my arrays and my for all loop and I just put it in on here.gpus.0, that's going to basically execute on my first GPU. So that slight little prefix, and again, I haven't had to change the signs of the code, and I've suddenly made it from a CPU computation to a GPU computation. Of course, here I'm only using one GPU across my whole node. So next one I'm going to show you is an example that just sort of gets everything up and running. I declare an array. It's stored on locale 0's memory because I'm running on locale 0 to start with. But then I'm going to use this coforall to basically spin up a task per node. So now I've got, again, my one task per node kind of node level parallelism going on. Then I'm going to use another parallel construct we haven't seen yet, a cobegin. This is basically a compound statement where each of the statements within the statement is a separate task. And so I'm going to have a blue statement here and a green statement. And so there'll be one task executing the blue, one executing the green. The blue corresponds to what I want to execute on my CPU. So on the CPU, I'm going to declare this array to B, initialize it to 2, and then copy it back into A, back on locale 0. So this gets all of the cores of my CPUs up and running because I've got the coforall across my nodes, and then I have these data parallel operations of initializing and copying arrays. So all my CPU cores are running. Then to get my GPUs running, since I have multiple GPUs per node, I'm going to use a coforall saying create a task per GPU on my node, migrate my task to that GPU, and then again, I'm going to declare some arrays, do some initialization, do some copying. Those are, again, data parallel operations, so I get all of the cores of my GPUs spinning up. So just by composing these simple things that create tasks, use on clauses, in a very compact amount of code, I can spin up a bunch of tasks to do a bunch of things. Not very interesting things in this example, trying to keep it, readable on a slide, but these same ideas apply. Well, yeah, the demo will show something more interesting. All right, so before I hand it off to Jade, just to kind of summarize what we've seen here. At this lower level, we've seen constructs for creating explicit tasks, the coforall loop that does it one per iteration, and the cobegin that does it one per child statement. We've also seen these notions for locality, the locales array, which represents all of our compute nodes, on clauses, which move computation around, ways to ask, where's my task running, or where's my variable allocated, and sublocales, which allow me to talk about locality domains within other locality domains. One more thing before I hand it off to Jade, I forgot about. So that's about all of the Chapel features I think we're going to show you tonight, other than maybe if Jade has some new things in the demo. But I want to say there's a ton you have not seen. So first of all, we focus predominantly on the parallel and locality features because those are the really unique things. But kind of all the things you normally want in a language are here as well. Object orientation, iterators, procedures with a bunch of features, namespacing, interoperability, yada, yada, yada. So don't fear that like it's all just about parallels and locality. And then there's even a bunch of parallel features we haven't seen, mostly around synchronization and some more high-level kind of abstractions for parallelism. And there's also a whole suite of tools that we're not really talking about tonight. So just wanted to kind of let you know about this landscape before we sort of stop telling you about Chapel in depth. And with that, I'll turn it over to Jade. Well, unless there are any questions. All right, I'm going to turn it over to Jade for the demo. And man, I used up way too much time. Sorry, Jade.
All right, let's see if I can switch this screen share properly. Yeah.
Are you expecting that?
Still have the Teams connection.
Still have the Teams connection. We are back and
The screen share to Teams.
need to change this to be that and share this as that. And now,
I got it.
oh, that's not the right screen yet.
Three finger swipe though.
This. I want you to mirror.
We did do this before you all.
We did test it.
This is also why I called Jade Abraham for doing the live demo. Although usually switching the screens.
There we go. Okay, so hopefully this text is big enough. There we go. Okay, so what I have set up here is I have two different windows that I will be demoing from. The first is this lovely VS Code window where I have the actual code. I also have this terminal on a, this is on a cluster with, I currently have 4 nodes allocated. Each node has 4 GPUs. This is a very similar cluster to El Capitan, which is the fastest supercomputer. It's got the same GPUs, same network, all that stuff. And over here, I have another terminal window. This is the exact same thing, 4 nodes, 4 GPUs per node, but this is NVIDIA GPUs, whereas this is AMD GPUs. And so basically, I can show you the exact same code is going to run on both.
I think in your terminal.
All right. So starting off, hopefully you're all now Chapel experts, and this code, make that a little bit bigger. This code should look mostly familiar to you. I'm going to pull in some modules here and see if we can fit that all on the screen here. I have my little function. It's a little sigmoid function. If you aren't familiar with what a sigmoid is, it's a in this case, a logistic function commonly used, as activation functions, smoothing values, all that fun stuff. This is a generic function that I've written here, and you can kind of see my editor is giving me hints about that. And I've declared that I'm going to take in this array, and it's generic over its domain, and I can query that domain, and it's generic over this element type, and I can query that element type. I'm then going to declare my result array to be exactly the same as my input array by just querying the type of the array. And so I have 2 arrays of the same type. Like you saw in the slides, I can move computation with on blocks. I can move over here to a single GPU. And then if you've ever written GPU code, the memories are distinct. You still kind of need to copy back and forth. If you were writing raw CUDA code, this would look like a CUDA memcopy. In Chapel, it just looks like an array assignment. So I can copy that data. I'll declare a result array. This time I use a slightly different syntax just to, keep things fresh and interesting. Rather than saying like array.type, the result type I'm declaring very explicitly using those queried values. So this and this are declared exactly the same. It's just one is declared in CPU memory, one is declared in GPU memory. I'll call a helper function to do my computation, and I'll copy the result back. This is kind of the core driver of the communication, but there's no real work. There's no kernels being launched done. That is done in this sigmoid function here. Again, written very generically. There's no types here, but at compile time, I can actually explicitly see, hey, look, these are explicit compiled types. So that's very nice, although rather verbose. And this right here is the entire computation and is a kernel launch. So this is and hopefully it's visible. This is a kernel launch. Instead of having to write a loop, I can use kind of high-level Chapel features to write this expression, and it just turns into a kernel for me. That basically gives me GPU execution here. The rest of this code is kind of to declare my array, fill up that array with elements, and do the computation. And you've got some extra if statements for doing printing. So I'm going to go ahead and build this. I'm using a package manager for Chapel called Mason to kind of drive everything for me, but I could conceivably just use the underlying Chapel command. But I'll go ahead and run this. And I can actually just run straight up like this, but I am going to make sure to print it out so we know that it's doing something. And we'll do verbose GPU so we can see that verbose output. And if I make this a little bit bigger here, so now you can see here, that verbose GPU output is telling me, hey, there's some copies going on, there's some kernel launches going on, and so I can actually see what the GPU is doing, and then I can get the results outputted. Obviously, these are random floating point values. They probably don't mean much to you, but thankfully, so I can run this. I can say print for GPU. Python is a lovely scripting language, and can make pretty graphs. I can type right. Nope.
Okay. You said it right.
Give that a moment. There we go. So I can open up write file. There we go. So, now I can prove to you that yes, it does, produce the sigmoid function. If I come back over here and I'm going to bump up the problem size here and run it with, sure, 10,000. Give it a second to run. And now we have a much more solid line as more points have been filled in. But as you can see, this is only ever driving one GPU, and I'm going to kind of progress through and make this computation a little bit more complicated as we go. So the next version of this code is going to use multiple GPUs. And so the core code will stay the same. So this sigmoid helper is going to stay the same for the rest of the demo. And basically what's going to change is this function here. So now what I'm going to do is I'm going to write my co-for-all loop like you saw in the slides. And I'm going to say I have some target locales that I want to compute on. And they could be GPU nodes. They could not be GPU nodes. And I have some standard library iterator that's going to chunk up my data for me so that I can split up the data between the GPUs. And then that's going to get iterated over in parallel, one task for each iteration. And then I will do that for each node. And then inside of that loop, the data copies stay the same. But what I'm going to do here is I'm going to take my original domain of the array, which is queried here, and I'm going to slice it based on the chunk that I'm currently using for the current iteration. And that gives me the local indices that this specific GPU should care about. And then I can slice and do the rest of the computation. And if I show this, you should be able to see a little clearly here, right? So I've got a domain over my indices, and I can just declare a normal array. But the rest of the computation pretty much stays the same. And if I go ahead and move over to that, I will just be able to run it. And probably run with verbose GPU so we can actually see what happens. And so now I have all of the GPUs on the system, which there's 4 of them, are actually printing out. So you can see here, different GPUs are doing stuff, and they're not printing in order because they're all being batched out in parallel. So
we're still on a single node here, though.
Yes, so we have not left the one node yet. I'm going to go ahead and switch over at this point to NVIDIA just to kind of prove, yes, it does work. We'll run Mason build. While we're waiting for this to build, does anyone have any questions so far? Yes. Yes. So there's this little print chapel end function, which I'll run here. And you can see there's, lots of details in here. The important bit here is I've said I'm running with the locale model for GPUs. I'm using NVIDIA GPUs. It's using CUDA 13. Over here, if I do the same thing, AMD GPUs, same thing. But now I can run it here and say run verbose GPU, and it works. If you need me to show you the code to prove to you it's the same on both machines, I can, or you can take my word for it. But exact same code, both machines. So now we can get into the distributed case. And what I'm going to start by doing is I have this multi-GPU kind of loop here, and I'm going to pull that out into a little function just to kind of keep the code a little cleaner. And so that is this sigmoid GPU function here. It's the exact same code on the previous slide, just kind of condensed into a single function, so it's easier to look at. And now the main sigmoid function, again, has another co-for-all loop. So now there's two co-for-all loops that are going to happen. And this one is going to go across all of the locales owned by my data. So the domain type in Chapel has as a method on it the target locales, which says who owns the indices. And so this will allow me to generically query where the data is stored and then move computation to it. So I can say, who owns this data, execute on all of those nodes. Then I'm already on that node, what are the indices that are actually present on my current node? I get that domain again, and then just like before, we call that GPU function, which is going to have another co-for-all. And this might get a little more clear, maybe not if I do this, maybe not. You can see like this here is a domain, plain domain. If I come down here, it looks like it's not going to tell me if it's distributed or not. So this kind of tool that I'm showing in the editor is one of those tools that Brad mentioned in the slides. It's kind of fun and fresh and new, and does not tell me about distributed types. But these are well typed to be distributed. But here, when I create this array, I'm using this kind of factory function. You saw create domain in the slides. This is create array, same idea. It creates my distributed array, and then everything else stays the same. So now, if I go into this folder, now I can start to run my code in parallel. So I can take this exact code here, and if I say Mason run, and I run it on one node, if verbose GPU, if I run it on one node, it will work the exact same as before, running on one node, multiple GPUs. But I can start to bump up the node size, and let's go straight to 4. Why not? And hopefully I fed it enough data and it won't crash. Yes. So now you can see it's these numbers over here on the left are the node IDs. And so I'm not only running on 4 GPUs, but 4 GPUs per node, so 16 GPUs. And I can, I'm only running with, I think, 100 elements. That's kind of tiny. We can run with lots more data and get something a little more interesting. But it'll finish pretty quickly because it's using massively parallel GPUs, and hopefully it won't crash on me. At a moment. Any questions before I go to the kind of last little segment here? Yes.
Yeah, so with the sigmoid and sigmoid helper, it's great that that you can express the type of parallelism that you want. And that it's relevant, it's fairly simple, it's sort of overreaching. But at the same time, I'm thinking, so it looks like the sigmoid helper, the kernel function, is within the sigmoid function, and it's kind of tightly bound. Like, I would wonder if, like, when designing a language, at any point in the last 30 years, were you thinking of having the expression of parallelism of the function and the expression of the kernel itself be less tightly coupled, or maybe each dangling off some main sigmoid function as an attribute or aspect or decorator, something like that.
So I'm very glad you asked that question because I'm just going to jump straight to the next slide, which might help demonstrate that a little bit.
Excellent.
We'll kind of skip this setup for now. And maybe these function names will give it away. I have this GPU function and I have this CPU function, and they are both calling sigmoid helper, the exact same function. One of them is running on a CPU and one of them is running on a GPU. So this computation is expressed generically, kind of, here's my science, I'm not going to change it. And when it's in a GPU context, it's a GPU kernel. And when it's in a CPU context, it's a CPU, multi-core parallelism vectorized thing. Does that sort of answer your question?
Did you also though change different computations within that? Like given the loop structure, like I want to do things other than sigmoid from one indication?
Yeah, I'm thinking mainly of decorators in Python, where you could say, I want to cache things this way, and it's just one additional line to your function.
Okay.
As loosely coupled as you can get it.
Yeah.
Yeah, I don't know that there's a great way to express exactly that.
I don't know. Where I was going with my question was, like if this felt like a lot of infrastructure that was at the end just kind of calling sigmoid and kind of too specific to sigmoid. I was gonna say one of the things you could do here is sort of extract a lot of that out into an iterator and then sort of like use the iterator to call sigmoid in one case and something else in another case or something like that. But anyway, sounds like maybe that's not what you were looking for. So
any other questions before I kind of show how this one gets set up? It's not too different from the other ones. So you've already seen kind of the secret behind this is that there's a CPU function and a GPU function. They will both be called. Again, this kind of co-for-all loop structure stays the same, but now I'm using a cobegin to say, run one GPU and one CPU and do them at the same time. And the way I'm doing that is I have this little helper function, which is going to take my indices and split them according to however I decide between these two elements. So go ahead and build this. And the way I've set this up is I have just a configurable GPU percentage that I can pass in at runtime to determine who gets to build the who gets to use the data. Let's do now. So if I just do kind of without touching anything, there we go. So you can see it's only 48 bytes or 56 bytes to the GPUs because I'm not using a very big problem size. So I'll first start by bumping up the problem size just a little bit, just so we don't have anybody not have any data to use. But then I can change, the GPU percentage. I don't really have a great way to show you that, yes, they're both working in parallel, but I will say, increase the GPU percentage to 80%. And we should see these numbers increase because we're now doing more work on the GPU.
Yeah, the reason we're only seeing the GPU stuff here is because you're using sort of the built-in like show me GPU related event feature. You could decorate your code with some write lines or something. So like, I'm a CPU doing this work, or I'm a GPU doing this work. But here we're just using the built-in features to trace events, right?
Yes.
Yeah.
Yeah. So one of the built-in features, and it's one of these libraries here, is GPU diagnostics, and say, dump out what's going on with GPUs. There's another similar one called COM diagnostics, which I didn't use, but could to show exactly, when communication happens between nodes. So that's a very useful tool for debugging, am I actually getting kernel launches? Am I doing too much communication? What's kind of happening in my program? And that is the end of the prepared little demo segment. Any questions for me before I hand it off to Brad to finish the slides?
If we can get it.
If we can get it back to the slides, yes.
Update's working and getting back to slides. Just to point out some things here. So I think it's notable that this ran on both NVIDIA and AMD with no source code changes, right? So it's not like I'm writing in CUDA for one and HIP for the other. So that's pretty huge. The other thing is that this stayed at the low level, right? So it was all with the coforals and ons and things. Something we've been working on, but not very hard recently, is having a distributed array like the ones we saw across top level nodes that can distribute across GPUs or across GPUs and CPUs. So you could write this as, a distributed array distributed across GPUs and CPUs, and now run my sigmoid across it. And that would be the same kind of thing that we started out with the for all loops and the distributed arrays, where all of the coforals or ons are kind of abstracted into that distributed array. It's just that rather than only targeting CPU data as we do today, it could target CPU and GPU. So that's ongoing work. So I clearly didn't practice this for time, or I didn't anticipate your questions or something. There's sort of 3 sections left, and I don't know that we need to do all of them. So I was going to poll and see what people are interested in. They're each pretty short, I think. One is about some applications of Chapel. The second one is showing you kind of resources and sort of, if you wanted to know more about Chapel, where should you go look? And the third one is a little bit philosophical and gets to things like, so why hasn't Chapel taken off like gangbusters and things like that? So of those, interest in applications, interest in the resources, less, a little bit, interest in the philosophical stuff. Okay, so I'll do a little bit on the applications. I'll probably blast through the resources. You'll be able to get these slides afterwards, and most of it. What's up? Or a photo, yeah. And I'll try to spend most of what time we have on the kind of philosophical stuff at the end. So applications, I mentioned that Chapel designed to be very general purpose. One of the things I'm really proud of is we don't just have like a killer app, but people have really used it from everything from computational fluid dynamics and aircraft design to simulating the universe to kind of computer sciencey things, data sciencey things, environmental things, and the kind of breadth of things that people have applied it to have really satisfied my sense that it is being used in general purpose ways. One of the cases I was going to zoom in on a little bit today is this project to basically look at coral reef biodiversity using satellite images and examining them. This was done by some colleagues of ours who essentially are working for NCAR, Seaworthy, and the Coral Reef Alliance. And so again, they're taking these high-res satellite images, running these little convolvers over them and seeing like how much biodiversity is there in this little circle over time. And they had previously been using Python and MATLAB. Chapel sort of was a similar level of expression, so it was kind of easy for them to get their heads around. And they basically were able to rewrite it such that a 10-day MATLAB run was able to finish in 2 seconds using 360 cores. So like, massive improvement. And one of the big things I wonder about is I feel like there must be many scientists out there kind of using Python and kind of just being very, very patient. And sort of like how many more of them could we get into Chapel? But maybe the cooler thing here was this first algorithm they did is kind of a fairly simple one. So it is order m by n by p, where m and n are the image dimensions, and p is sort of the pixelated circumference of the circle that they're convolving across it. But the one that they really wanted to do all along was what they call spectral diversity. It's m by n by p cubed. But because their original one was taking 10 days, like they never thought they would be able to do this. And once they got it down to 2 seconds, they're like, oh, maybe we could do that other algorithm. Initially, they were like, well, it seems like that would take us about 4 weeks on an 8-core desktop. But this was right around the time the GPU features were coming online. And so one of the first things we did was work on porting this over to the GPUs. It required adding about 90 lines of code, so it was up to 320 lines of code, still a very small code. And we ran it on Frontier, which was, I think at the time, the #1 system on the top 500. Now it's the #2 using NVIDIA GPUs. And basically, we're able to get it to run in 87 minutes on 2 nodes, which is 16 GPUs. And, oh, I'm sorry. No, yeah, you're seeing what I'm saying. And in 17 minutes on 64 nodes. There's a little speed up graph here, and it's clearly not linear speed up. And I think more could be done there to improve it. And again, this was in the early days, so it may have gotten better since then. But at the same time, it's like they were still getting benefit as they added resources and got it down to a tractable amount of time. One of the things I like about this code is it's really, I think, the smallest killer app of Chapel so far. Like 300 lines, if you think about it, is really, really modest. And they were able to do things that revolutionized their science. We've got an interview with the developer who did this up on our blog, and he talks about, what a game changer it was for them. On the other side of the spectrum, the largest application written in Chapel is over 100,000 lines. And this is this computational fluid dynamics framework that was written at Polytechnique Montreal in Canada. And this is a kind of small, modest academic group that has basically developed now a world-class CFD framework in just a few years due to Chapel revolutionizing things for them. So there's some quotes from their PI where they had students whose master's projects would have taken them 2 years before. Now they could do it in 3 months. I think the quote here talks about how undergrads were able to contribute to this project for the first time. And again, they credit Chapel with that, where C++ and MPI and OpenMP is what they would have used otherwise. And the last one is an interesting case. It's a kind of medium-sized code, about 5,000 lines. And this is a researcher who doesn't even really care about scalable parallel computing or HPC. He just got to the point where he's like, I like this better than Python and Fortran just for my desktop computing. And so it's become that for him and for some in his group. So again, kind of a smaller scale system, a medium scale code, but a very different use case. Each of these are from these interviews I mentioned. There's actually a bunch of these interviews. If you're interested in reading more about users' experiences, what are they doing, what do they like, and even what they don't like, this is a great series to look into. All right, so that was my applications section. We're doing okay. For resources, I'm going to blast through these pretty quickly. Where does Chapel run? Well, pretty much everywhere. Bunch of different CPU vendors, bunch of different GPUs, bunch of different networks. You'll notice this isn't complete. Like, we don't run on Intel GPUs or Apple GPUs yet. But there's no reason we couldn't. It just hasn't been a priority yet. So we're very, very portable. As far as how you can get Chapel, there's a ton of release formats you can get it in. Docker, Homebrew, Linux packages, SPAC, which we use a lot in HPC. And the link to where you grab those is here. There's a bunch of ways to engage with the Chapel community. We've got live meetings, weekly meetings, both kind of just normal project meetings and then deep dives. We have an annual conference where people can talk about what they're doing. Got a bunch of electronic communications, and then a bunch of social media channels, discussion forums, ways to get started. So, if you've got a favorite platform, we're hopefully there, reach out and ask questions or whatever. And then some of the news since we last talked to you, we've done this 2.0 release. In terms of semantic versioning, this is like our 1.0 release. We had an executive who forced us to go to 1.0 arbitrarily at some point in the past. But in this release, we basically claimed we were going to stabilize the core language and library features, mark those that were not stable as being such. And we're now using an additions discipline like in Rust to introduce new breaking features or new features in a way that's not going to surprise people. You can read about the 2.0 release on our blog. And then I mentioned earlier, we joined HPSF, which again is this foundation within the Linux Foundation. It's all about open source HPC software. There are a bunch of sponsors, including locally Microsoft, AMD, NVIDIA. And we became a member, again, just about 6-7 months ago. And as part of this process, things like our weekly meetings went from being internal to HP to being community meetings. Our governance is moving to a community model. It's now done in the open. We're working on how do we bring new people into it. A bunch of our repos became public that weren't before. And so it's really helped us open up the project. They're doing an annual conference, a live conference once a year. That usually falls, I think, in March, April timeframe. Jade spoke there this past year. And then they have biweekly meetings of the Technical Advisory Council, which anybody can attend and just sort of hear about kind of business on a biweekly basis. And there's also a board meeting, which as far as I know are open. I've never attended those myself. Yes.
One is doing like CI for HPC, and another, which I've been involved in, is doing like performance benchmarking for HPC. I think there's a new one for application binary. I'm not really sure what they're doing, but
I'm not even.
They're meeting and they're discussing.
Yeah.
And those are all public and bi-weekly.
Yep. And there's also a Slack channel. Anyway, if you want to know more about HPS, we can help hook you up with them. It's a great organization, and a lot of great projects have joined it. Any other questions before I go to my closing thoughts? All right, this is the slightly philosophical part. I guess I first start with a summary. I'll just say at a high level, parallel programming traditionally requires us to mash a bunch of notations together for all the different kinds of hardware we're targeting. Chapel's unique in that it tries to do all of that in one language that's optimizable, portable, performant, as we're seeing, maybe energy efficient as well. And I've told you briefly that users are benefiting from it. All right, so my first kind of philosophical slide here is about AI. So often when I give this talk nowadays, people will say, well, gosh, I mean, AI is doing all the programming these days. Do we really care if it's Chapel or something else? Does Chapel still bring value to the table? And
Is Claude Code.
so, I mean, it's at least somewhat familiar, but more importantly than that, Claude Code with like the model context protocol is really good at learning new things through pattern matching. And so even though it may not have the corpus of programs in Chapel that it has in C++ or Python or whatever, it seems to be able to create these mappings where it's like, well, I know what the game of life is from Python or C++ or whatever, and I know how Python features map to Chapel features, and it has done some pretty amazing things. Typically with the MCP involved, so that has tooling to kind of guide it and say like error, syntax error, and it'll back off and try something else. But it's been kind of remarkable. I was pessimistic about Claude's ability to do these things, and it's done some things that have surprised us, I would say. Anyway, I don't claim to have a definitive answer to this question, but I'll tell you my opinion is that I think languages like Chapel definitely still have value, at least for the future that I can foresee. And I have kind of two parts to this answer, or two rationales, if you will. The first one is a little bit speculative on my part, and I'm not an AI expert, but I think an AI is going to do a better job of targeting a unified, well-designed parallel language than it is this kind of mashup of all these low-level things. Just because, as I was talking about, like if it's mapping sort of like these kind of algorithmic patterns and these kind of concepts, and it's sort of like one language is trying to map it to, I think that's going to have a higher success rate than like I have to be able to map it to C++ and MPI and OpenMP and CUDA. So that's my kind of the bet that I'm kind of making. But I think more importantly than that, even if it were sort of no better or maybe slightly worse, to the extent that we as humans have to keep looking over its shoulder to check the work, understand it, maintain it, would you rather be sort of understanding it and checking it in Chapel or in SHMEM or MPI or CUDA or whatever? I'll say that this SHMEM is actually pretty clean code. SHMEM is pretty nice to begin with, and this is using some nice abstractions. This doesn't have any CUDA or multi-threading or anything like that, which would make it worse. So I would say, I mean, I'm obviously biased. I know Chapel well, but I think that high level is going to really benefit the human operator that's collaborating with the AI, at least until such a day that we just don't even bother checking AI's work anymore. But that day scares me.
Chapel was a whole lot less tokens than
That's a good point. Need to update my slide to include that. So this gets back to the question you were asking earlier. And I want to correct one thing. You've said 30 years a couple times. So I've been in this business for 30 years, but Chapel's only more like 20 years old. So we don't want to like, no, we don't want to like give it that much time. Anyway, so yeah, so if you're coming out of this talk like, yeah, this sounds really cool, like why hasn't it taken over the world, which is more or less what you asked earlier. What's the catch? What are you not telling us? Which I'll also phrase as what keeps me up at night. So I'm going to call out kind of three things here that are sort of like, like trying to be totally straight up and honest with you. The first one is adoption of Chapel is a real challenge. And to some extent, adoption of any new language is a challenge, right? You're trying to build a community out of nothing, get people on board and get enough of them on board that it keeps sort of snowballing and growing. And that's always challenging. And I think it's particularly challenging nowadays that we have a lot of really great languages where Python, Rust, Swift, and Julia kind of come quickly to mind for me. Like people aren't sort of suffering so badly that they're out shopping for languages a whole lot. And on top of that, we're all about parallel computing and particularly scalable parallel computing, which, people are interested in, but not nearly as many as are just on desktop computing or whatever, where frankly, our modern languages do a pretty decent job with parallelism compared to where we were 30 years ago. So this is a real challenge. And for each of these, I'll tell you how I get back to sleep or why this maybe doesn't completely destroy me. For me, I think one of the things that's really encouraging is users like Nelson who are using Python or using Fortran, and yet they're seeing value in Chapel even without the large scale parallelism. And so the question is, how do we build more Nelsons, or Scott who did the Coral Reef code? How do we find more Python programmers who are like, oh yeah, I could do that language, and gosh, I'd get that kind of performance or scalability. Yeah, I would invest in that. So the second thing relates to technical debt and incomplete efforts. There's, as we were talking about, Chapel's 20 years old and its code base is 20 years old in many cases. There are a lot of language features and libraries that feel rock solid, and there are other ones that feel squishier and a little bit like, and it doesn't take very long experimenting with language to wander off into some of those squishy areas. Meanwhile, we're finding a lot of our time more and more is going into preserving the portability we have and tracking the third-party software we rely on. Jade does a lot of this. That's why they're laughing. Jade, I mentioned, gave a few talks at HPSFCon. One of them was about technical debt and keeping up with new versions of LLVM, new versions of GMP, new versions of, yeah, JE Malloc. Yep. And not in, yeah, right. So this is all very scary. The way I sort of reassure myself here is I think it's the nature of software particularly software of our maturity, I guess you could say, and open source projects in general to kind of be like this. I've also seen how quickly things can improve with effort. So as an example, we have a package manager, Jade was using it earlier. It's developed by an intern many years ago. It's mostly not gotten any attention. It's never worked very well. Just in the past couple of months, Jade has put in an effort and gotten it really up to snuff. There's more to do still, but like it's a game changer in terms of a relatively modest amount of effort. And so when I think about like if we could get this to catch on, if we could grow the community, more efforts like this could go on and we could get to a better place. The third thing though that keeps me up at night is funding. And we're a project that has been lucky enough to enjoy long-term stability and growth in funding, but that's recently stalled and even reversed. Our team has shrunk for the first time ever. And at this point, without new sources of funding or staffing or collaboration, we expect to go into maintenance-only mode this coming fall, and we published a blog post about this recently. Unfortunately, I don't have a way to get myself back to sleep on this one yet. This actually does keep me up at night these days. So if you happen to have a friend who's excited about this kind of stuff and has deep pockets, or if you work for a company for which it's like, oh, we'd like to collaborate on this, or we'd like to invest in this, or contribute to it, these are things we would love to hear about this year. We would love for that to happen. At this point, most of the community that we've engaged with seems so focused on AI that it's really hard to get people to sort of focus on languages and parallelism and scalability.
We would
But
love for that. I was looking for.
Well, so we are doing what we can to beat the bushes and spread the word. And if you know of people who you think would be interested in contributing or collaborating, like, right, it doesn't have to be about giving us money. I think I kind of said that here, staffing or collaboration, right? If you know of people who are like, yeah, I think they would be interested in collaborating on this or contributing to this or whatever, like that's something we'd be very interested in for sure. Not just money, but money would be great. Money's always great, right? All right. If you want to know more about Chapel, there's our website, our blog. You can reach out to the team and community. If you want to know more about applications of Chapel, the 7 questions for users interviews I showed you earlier are great. If you want to hear me more grappling about like language adoption and the complexities in that, I seem to write about this a lot, and that's all on our blog as well. This first one is actually where this talk started, about looking back those 30 years in written form, and it goes into more depth than I got to here. And this other one's about kind of about language adoption and sort of 10 things we hear where people say, well, it'll never succeed because of this or that or the other, and sort of my rebuttal to that, essentially. So if you like wrestling with those kind of questions, this is a place to spend some time, or have your AI read it and tell you what it says. And just to wrap up, I'll say that I consider both current and aspiring parallel programmers, and particularly scalable parallel programmers, to be at least as worthy of modern languages as the Python, Rust, Swift, and Julia communities are. Again, languages I think are really notable in their sort of modernity and their ability to catch on, but I would say none of which are ready for large-scale parallel computing. And that over the next 30 years, as opposed to reflecting the past 30, I hope we'll see the number of broadly adopted languages for scalable parallelism to be at least 1 rather than the current 0, and MPI and CUDA and OpenMP and all that stuff. So that's it. Thank you for letting us use up the whole time. And thanks for your questions and interest throughout it. And I hope this has been interesting. And we can hang around if people want to chat more. But yeah, that's officially the end of the session, I guess. So.
Yep.
Yeah. Great.
Thank you very much for presenting.
Yeah. Thanks again for having us. Yeah. We appreciate it. It's great to be here. So. All right, there you go. Yeah. Again, anybody have any other questions? I mean, I'm happy to hang out as long as you want to, but also if you're ready to go home, totally understand that as well.